Hello students, we're going to go over D.2 question practice problems 1 through 5. Okay, so I'm going to show you how to do these questions, the equations needed for each of the questions. You'll need a calculator to do the calculations yourself, and you can always check the answers with the answer key that's available online. Number 1, so zoom in here. Number 1, 2-point charges of equal magnitude are separated by an air gap of 5 centimeters. The force between the charges is 0.8 millinewtons. Determine the magnitude of each charge. Okay, so we're given two pieces of information here. We're given the distance between the charges, and we're given the force. So we're going to, if I draw a picture, and I'm not going to draw a picture for all of them, but if we have two forces, if we have two charges, Q1 and Q2, we know that the distance between them is needs to be converted to meters. Okay, so everything in these equations need to be converted to meters. For distance, which is r, everything needs to be converted to coulombs for charge, which is Q1 and Q2. In this case, they both have the same charge that's stated in the question. And then newtons has to be in, force needs to be in newtons. So let me double check the force here. The force was 0.8 millinewtons. So the electric force is given as Fe equals 0.8 times 10 to the -3 newtons. Okay. All right. So this is pretty much you're just plugging in the numbers here. I'm also going to write down that Q1 equals Q2. We're not given any information about the charges other than that they're equal. Just double check here. 2-point charges of equal magnitude, yeah. It doesn't even give us the sign of the charges. So if they're, but if they're equal in magnitude, we can, if they're equal in magnitude and also equal in sign, they will repel each other, right? So the force of Q1 would push the force of Q2 would push Q1, and the force of Q1 would push Q2, and they would be separate if they're like charges. If they're opposite charges, then they will attract. Okay, so then if they're like charges, they will attract to each other. And that force needs to be, the force between them needs to be equal, even if the magnitude of the charges are not equal. For instance, like if Q1 was twice as much as Q2, they'll pull on each other, but because of Newton's third law, for every force, there's an equal and opposite reaction force. So like if Q1 pulls on Q2, Q2 also pulls on Q1 at the same. All right, anyways, we're going to plug in all of our values here. So again, there's gonna be a lot of errors here. This goes in here, and now for K, which I guess I can move it over here so that it's easier to show. For K is a constant. Okay, there's a couple things about K we need to know. It's a constant, of course, so you just plug in this number, 8 times 9 times 10 to the 9th. And the unit is not really that important. It's newtons per meter squared, coulombs squared. It's not, it just makes the equation work. Our equations sometimes need these constants, or a lot of times need these constants to make the relationship true. Okay, so we've converted everything to the correct units. We plugged everything in. Once you plug everything in, you're going to get a value for Q1 times Q2, and then you should square root it. So if I were to simplify this, let's see here, Q1, so Q is would be equal to the charge of either, so I'll just say Q, is equal to the square root of Q1 times Q2. If you think about it, this is true because they're the same number. So like 2 times 2 is 4, and square root of 4 is 2. So whatever you get here for Q1 times Q2, you're going to square root it. Okay. Part B, what if you increase the distance to 0.1 meters? Okay, so now you're just going to take everything in your equation and you're just going to change the distance, the R, so this is the R, to 0.1 meters, and then you're going to solve for the force. Now that you know the charges, you can solve for the force. And again, it doesn't tell us if the force is attractive force or repelling force, but that doesn't really matter in the question. If I read the question, it says calculate the force between the charges. Their separation is increased to 10 centimeters, which is 0.1 meters. It doesn't say the direction of the force. If we assume that the forces are, if the charges are positive, you know, they would repel each other. Oh, you know what? So actually, because we know that two charges are equal, well, this is equal in magnitude. It doesn't say equal in direction. Okay, so yeah, we don't know. The space between the charges is filled with a material permeability 1.8 times 10 to the negative 11. Okay, so this part of the equation, this part is interesting. Now K can be defined as, or as 1/4 pi over the permeability constant. So K is a constant that can be calculated with another constant. This permeability constant is a property of where the electric field is, like the space the electric field is in. So how does the electric field permeate through a certain area or space? So that can change. We're going to basically, you're going to calculate a new. So this is this would be part B2. This is part B1. You're going to calculate a new K constant. So we're going to put in the number. So what's the number? 1.8 times 10 to the negative 11. Okay, so here, I'll just write it over here. 1/4 pi times, I already forgot the number. It is 1.8 times 10 to 11. 1.8 times 10 to negative 11. And I don't really care much about the units here, but yeah, it's just the same units, but the inverse, right? So the units are coulombs per newtons per meters squared. Okay, all right, great. But anyways, I'm just going to plug that in here, and I'm going to get a new K constant. Okay, so you're going to put that in your calculator. All right, question 1, a little bit lengthy. Question 2, so the questions get a little bit shorter here on out. Question 2, we have two charges. So this is pretty straightforward. You're given the two charges, 5.6 times 10 to the negative 7, and negative 1.2 times 10 to the negative 6. So I see the opposite charges, so they're attract. And we get a distance that we have to convert. 45 millimeters is 0.045 meters. Calculate the force. Just plug everything in. Make sure to use, in this case, make sure to use 8.99 times 10 to the 9th for the K constant. And then what are we solving for? We're solving for the force, correct? The magnitude of the force. So F equals question mark. And then we do know that there's attractive force. So it's a force that's pulling the two charges together. Part B, calculate the distance when the charges between the charges at which the force is 1. So again, you're just really just plugging into this equation again, and then you're solving for R. Doesn't seem like anything that different from what we're doing, other than, I guess, we're solving for R this time. So that's part B. Number 3, nucleus of gold has a charge of plus 79 electrons. Okay, so when I read that, I see that that's the charge and it's positive. So E is just basically the magnitude. And the magnitude of E is 1.6 times 10 to the negative 19. And then the distance, the radius is 7 femtometers. Okay, femtometers is 7 times 10 to the negative 15 meters. All right. So I already assume that I'm going to need the charge of the nucleus. So I'm just going to take 79 times 1.6 times 10 to negative 19. Here's the equation we're going to use for this. So electric field strength, we'll say, is basically the same equation as electric force, but now I only have one charge. The reason why I only have one charge is because if we're looking at the field around one charge, the distance from that one charge will tell us a certain strength. And the farther away we get from the charge, the less the strength. Okay, that's all that really matters. In this case, the second charge is not what we're worried about. We're worried about the first charge and only the first charge and what the field around it is like. When you put something in that field, then you can figure out, oh, the field would be this strong in that area, but we're not worried about what it is that we're putting in there just yet. We're just saying, here's the field and how far away is an object in that field. Okay. So we're going to plug in for part A, it says to plug in 1.5 radii from the center of the gold nucleus. So actually, I believe I might have put this over here. Huh, interesting. So 1.5 radii would be this number. So we'll move this over here. And then I believe I'm just going to put that in. I have the charge. So I'm going to put this charge into here. I know my K. Here's my R. And then solve for E, I believe. Let me double check. Yeah, the field strength. So just what is E equal to? E equals question mark. Okay, so this is just more calculations. Don't forget the square, the radius. Don't forget to put in your exponents. Use parentheses. So yeah, a lot of parentheses, a lot of exponents, a lot of different numbers and scientific notation. So just be careful. And then yeah, 1.5 radii. You're just going to take the radius that they give us and multiply by 1.5. Part B, it says a free proton. Okay, so it's a single proton. Here, I'll zoom in. That is also 1.5 away. Calculate the force. Okay, so you're just going to use the same number here for radius. 7 times 10 to the 15. You're just going to use that same number, so that's why I had it there. And then, yeah, you're just going to plug in the charge for proton and the charge of the nucleus. Now, yeah, just make sure you plug in the right number. This one goes in for, we'll say, Q2. And then this one can go in again for Q1. Radius is still the same. It's because now we've put an object in the field, we can now calculate the actual force between the two objects. Okay. That was number 3. Number 4, the magnitude of the electric field at a distance of 0.25 meters and the charge. Now we're given the electric field strength. Notice that the electric field strength is newtons per coulomb. When we talk about electric field strength, we usually like to talk about how strong is that field per coulomb. The field is directed towards the point charge. Calculate the value of the point charge, including its sign. Okay, so I'm not going to really spent a lot of time on this because it's the same equation again, but for electric field, and we have just two things put in here. Now, the electric field, um, the electric field given is positive. I don't see why the charge wouldn't also be positive, unless it says something like the object that creates the field is positive and there's an attraction, then you would know that they're opposites. But we're not given any information like that in this question. We're just given a positive point charge in a distance. The field is directed towards the point charge. Oh, okay. So they could be talking about field lines here. Okay, well, this is a good time to talk about field lines. So if we're talking about field lines, field lines basically between a positive charge and a negative charge, field lines come out of the positive and go into the negative. Okay, so all field lines come out of positive and negative. Now some these also curve here because there's point charges. I didn't give myself a ton of space here, so let me give you more space. So yeah, so on the outside edges, so on these edges, it curves like this. Now, one thing that kind of students are interested in is the field does this thing where it comes out the other side too. It goes in the other, so it's like it does this thing where it comes all the way out and goes back in like this. So that's why we need more space. But like in a way, this is going out like this, and this is coming in like this. So, anyways, the question could be saying, this is kind of vague, to be honest. It says calculate the value of the point charge, including the sun. The field is directed towards the point charge. So if the field is going into the charge, then we know that it, in this case, it could actually be negative. This one. So I'll explain my reasoning here. So if the field goes into the point charge, it's negative. If the field comes out of the point charge, it's positive. So I believe the charge should be negative in this case. Okay, it's entirely possible that because the question is vague, it's not doesn't actually matter that much. But okay, number 5 is another just plugging in numbers. We've got the electric field strength and the charge. So now we're going to solve for R. R equals question mark. Don't forget the square root when you do this. So basically, just make sure I did this correct. Multiply both sides. Oh, I don't know why I wrote my equation like this. Just multiply both sides by r and square root, divide by e. Make sure e is inside the radical, and then solve for r. Let's read the question again just to make sure we've got everything. Yeah, it's a really short question, so that one doesn't seem too complicated. It's just more practice, basically.